Hello everyone. Today, I'm going to talk about the future of NPUs, the dedicated AI cores that are increasingly being integrated into modern CPUs. Here is the table of contents. After reviewing the overall characteristics of AI, we will look into NPU-specific issues. AI cores, also known as NPU, first made headlines when Apple included them in their chips as a distinct feature separate from the GPU. Since then, Intel and AMD have followed suit with small AI cores of their own, and the latest Ryzen AI 300 series and Lunar Lake chips feature significantly larger ones. Currently, mainstream AI still relies heavily on the cloud. So, what exactly is the point of these on-device AI chips? Let's break it down. First, let's look at the strengths of running AI locally. As I mentioned, high-utility models tend to be massive, trained on enormous amounts of data. These giant models require extreme machine power, huge memory and processor that personal PCs and smartphones simply cannot match. Therefore, for an NPU to be useful, it needs to provide value even with lower performance specs. The first and biggest advantage of local AI is that data processing is completed entirely within the device. You can process confidential business documents, personal photos, or biometric authentication data without ever sending them to an external server. This drastically reduces the risk of interception during transmission or leaks from the server side. Local processing is crucial for complying with strict data protection regulations like the GDPR. In fact, the reason Microsoft requires an NPU for their Copilot+ PCs is largely due to this high demand for security in business environments. Secondly, on-device AI have the advantage of low latency and real-time performance. When you send data to a cloud, there is always some latency or lag. These lag can be fatal in real-time tasks like autonomous driving, factory robot control, or image upscaling in gaming. For those real-time applications, on-device AI is an essential technology. The third advantage is that it doesn't depend on the communication environment. It works in area with an unstable connection like mountains, at sea or underground, and remains functional during disasters when networks might be down. It is also unaffected by server downtime or network congestion, making it vital for tasks where stability is key. The fourth advantage is cost reduction. Depending on the use case, local execution is often cheaper. This applies when the data traffic costs are high compared to the processing load, or when the hardware usage rate is constantly high. A prime example of this is edge AI, such as video analysis for surveillance cameras. Before we look at on-device AI specifically, let's quickly review what AI is used for in general. Current AI can basically be understood as a system that creates a flexible and universal mapping between any given pair. Thinking of it this way makes it easier to understand its applications. This mapping isn't just crudely memorizing pairs, it fills in the gaps using interpolation. This is what dramatically increases AI's practicality. For simplicity in this video, we will focus on this aspect. We can categorize AI into three types based on how it maps inputs to outputs. These are classification, translation, and generation. First is classification. This is where the input information is large, but the output information is small. Research that serves as the root of modern deep neural networks began with handwriting recognition. This takes handwriting, which varies wildly by writer and condition, and converts it into at most about 100 ASCII characters. Other examples include voice recognition and separating a person from the background in an image. Next is translation, or what we might call modification. This occurs when the input and output have similar amounts of information. Early developments included noise removal from images and audio, or enhancing voices and faces. In smartphones, this type of AI is used extensively to compensate for small camera lenses. Apple's Deep Fusion is a prime example that highlighted the importance of NPUs. Nowadays, using large language models to fix grammar or translate text has become a daily task for many. The last is generation. This is when the input information is small, but the output is large. Just by typing a simple text string, you can generate rich images or even video. A key characteristic of generative AI is that for one input X, there are multiple possible outputs Y. The key challenge here is how to narrow down and select the most appropriate answer. For instance, many of you might remember early image generative AI like Google Deep Dream producing strange, unnatural images. In the early days of practical image generation, generative adversarial networks were often used to solve this. This method essentially involves the AI generating an image, and then another part of the AI judging it and rejecting unnatural results, repeating the learning process. Similarly, large language models are trained to predict the next word in a sentence. But if used raw, they tend to output strings of associations that are grammatically correct but logically meaningless. That is why supervised fine-tuning is essential to teach the model to choose the response that best matches the user's question. Next, let's think about local AI specifically. First, realize that training and inference place completely different loads on hardware. Training is like compiling a dictionary. It requires collecting massive data and constant adjustments, using huge amounts of GPU and memory. It is generally not meant for local execution. Inference, on the other hand, is like looking up a word in that dictionary. The load per action isn't that heavy, making it viable for local execution. Practical local inference models appeared in a specific order: first classification, then translation, and finally generation. Classification AI works well even with relatively small models. It has been quietly used in devices without keyboards for character recognition, voice recognition, and Face ID. Things like Google Lens text reading now run on almost any smartphone. Translation AI varies quite a bit. While things like Apple's Deep Fusion fit on a phone, high-precision translation using large language models is still mostly done online. Generative AI requires fairly large models to be practical, meaning you need a bunch of memory. For example, Intel's AI Playground app, even in its simplified version, requires about 8 GB of disk space. Since the performance is often underwhelming at that size, most people still use online services. NPUs become cost-effective compared to the cloud when used for edge AI or tasks with high hardware utilization rates. Microsoft is already running features like background blur and live captions completely locally. In the future, things like IME predictive text, document proofreading, or even NPC dialogue in games could be handled by local LLMs. Also, handling pre-processing locally to reduce the load on cloud servers is a very likely use case. However, recent techniques like quantization, which lowers calculation precision, and distillation, which uses existing models to teach smaller ones, have allowed us to drastically reduce model size while maintaining performance. Now, if you have a consumer machine with 16 to 24 GB of memory, practical generative inference is becoming possible. Next, let's address a common question. Can't GPUs do everything NPUs can do? Until now, GPUs were the main drivers of AI processing. This is because both 3D graphics and neural networks rely heavily on weighted addition and multiply accumulate operations, so the circuits could be shared. However, while similar, GPUs and NPUs are different. Computer graphics involve loading various objects, performing 4x4 matrix operations, and writing results back to memory. GPUs are optimized for this specific flow. In AI, it is common to perform cumulative operations on 256 to 4096 variables. Since the same data is reused throughout these calculations, mechanisms such as systolic arrays have been introduced to reduce data transfer with memory and improve energy efficiency. If you ignore efficiency, a CPU can do any calculation. A GPU can handle AI just fine. But the purpose of an NPU is to maximize efficiency. That is why smartphones have dedicated circuits, and why Google, who has a team designing server chips, builds dedicated AI chips for their servers. Finally, let's look at the ecosystem for using NPUs. For standard graphics, we have established common standards like OpenGL and DirectX. Drivers and applications are built around these standards, so users rarely have to worry about hardware differences. However, the AI field is different. Currently, vendor-specific environments are mainstream. NVIDIA has CUDA, AMD has ROCm, and Intel has OpenVINO. These lack sufficient compatibility. It is not rare for an app to run only on a GPU despite an NPU being present, or for software to fail on the Snapdragon X Elite. To solve this, there are candidates for a common platform, such as DirectML, ONNX, WebNN, and PyTorch. Unfortunately, we are currently in a state where multiple candidates are fighting for supremacy, and no definitive standard has emerged yet. In this chaos, Microsoft is moving to take the lead in local AI. They are trying to build a common infrastructure using vendor-agnostic platforms like DirectML and ONNX. Microsoft's official documentation suggests they aim to build an ecosystem centered on their own platform. On the flip side, for companies like NVIDIA and Intel who already lead the ecosystem, Microsoft's common platform represents competition. Interestingly, the certification for Copilot+ PCs proceeded in reverse order of vendor strength. First Qualcomm's NPU was certified, then Intel and AMD. NVIDIA's GPU support was announced but has seen little progress since. This delay likely stems from the rivalry between Microsoft and these hardware vendors. The summary. We have briefly looked at the current landscape of NPUs, but to be honest, the software environment remains immature. We have yet to see a definitive middleware like DirectX, and simply buying the latest Windows PC doesn't mean you can fully utilize the NPU. My personal prediction is that we won't see true practicality until around 2028.